All right, now we're going to review chapter 16, which is about random variables. So first let's discuss some terminology. What is a random variable? That is a variable that can take on numerical values describing the outcome of a random process. So for example, we could talk about a random variable that represents the outcome of rolling a die. A probability distribution, also called a probability model, is a table that lists all the outcomes a random variable can take, along with the associated probabilities for each outcome. The probabilities have to add up to 1 because you have everything. So for the die that I just mentioned above, the table would list that the outcomes can be 1, 2, 3, 4, 5, and 6, and underneath that the probabilities for each one. So the probability of rolling a 1 is 1, 6, 2 is 1, 6, 3 is 1, 6, so on and so forth. Now, random variable notation, capital letters are used for the variable. So like we could use the capital letter X to represent the outcome of rolling a die. And then a small x, often with a subscript, is used to represent an individual outcome. So we might have x sub 1 representing the first outcome, x sub 2 representing the second outcome, so on and so forth. Now the probability of big X equal little x is the probability that the variable takes on the value little x, or whatever that outcome might be. So we might say, what's the probability that big X equals 1? So that would be the probability of rolling a 1, so on and so forth. Okay, now there are two different kinds of random variables. There's discrete and there is continuous. First, let's talk about discrete. Discrete random variable, the probability distribution is finite. In other words, there's a finite possible outcomes. You can list them all. So that would be like rolling a die. There's 6 different things that can happen. You can definitely list all 6. Okay. If you find the average for a discrete random variable, that's called the expected value, and it represents the long run average, or what you would expect to happen in the long run, right? So if we were to calculate expected value for rolling a die or something like that, you might use the symbol mu, Greek letter mu, for mean, or you might see capital E of x. Either one, they mean the same thing, expected value or the mean of the discrete random variable. And the way we calculate that is it's the sum of each outcome times the probability. So for in the example I was just talking about with the die, the first outcome is rolling a 1. It has a probability of 1/6. So 1 times 1/6, plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. Add all that up, and you would have what you would expect to happen, the long run average of all the different outcomes of rolling a die. Okay. We also can calculate spread for this distribution, right? We can calculate variance or standard deviation. And so the formula for variance, which is just a square of the standard deviation, is you find each deviation, so like how far the first outcome is from the expected outcome, that number squared, times the probability of that outcome. Okay, plus the second outcome minus the mean outcome, that quantity squared, times the probability of that second outcome. So on and so forth until you get all the outcomes. At the very end, take the square root and you'll have your standard deviation. So let's actually do that for our dice. So the expected value would be 1 times 1/6, right? Plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. So we get an expected outcome, or a long run average, of 3.5. Right, so that's just the average outcome in the long run of repeatedly rolling a die. Now to find the standard deviation, we start with the variance. So again, looking at the formula here, we want to do value minus mean squared times the probability. So 1 minus 3.5, 1 minus 3.5 squared times the probability, which would be times 1/6, which would be the same as just dividing by 6, right? And then I want to do that for the next one. So 2 minus 3.5 squared divided by 6, because that's the same as times 1/6, so on and so forth. Okay, so I can go through and do that whole thing, and then I'll have the variance, take the square root, and I'll have the standard deviation. There is a shortcut, and that is to put the data into lists in your calculator. Clear, enter, clear, enter. Okay, so we will put the different outcomes in list 1. And the corresponding probabilities in list 2. One more. Okay, once you have those in your list, then you can go to stat calc 1var stats, and I've got a bunch of stuff on my screen there, so let me clear that out first. Okay, so stat calc 1var stats L1 comma L2. And so here is the expected value, and here's the standard deviation. Okay, and of course if you need the variance, you can just square that to get the variance. And then there's some other numbers down here as well. You'll see there's the minimum, your quartile 1, median, quartile 3. So you got your 5-number summary there as well. But the main ones you want for random variables is the expected value, which is the mean, and the standard deviation. Okay? All right. Now, if you have a continuous random variable, that means that these can take on all values in an interval. There are an infinite number of possible outcomes, right? Because you could be anything from 1 to 2, for example, including any decimal variation in there. So there's really an infinite number of outcomes possible. Their distributions are density curves, such as the normal model. If a normal model is appropriate, and those are mainly the ones that we looked at in AP Stats, then you can use z-scores in a z-table to find areas under the curve to represent the probabilities. So then those problems become just like Chapter 6 problems that we've already reviewed. Okay. So a couple other things we talked about in Chapter 16, though, is transformations of random variables. So a random variable y could be a plus bx, where x is a random variable x. Okay. So if we are taking a random variable and we are multiplying everything in the distribution by something and then adding something to everything in the distribution, right? That's a linear transformation. The mean, how does it change? Well, we kind of talked about this already when we talked about transformations back in Chapter 6, right? So the mean, it'll get multiplied by whatever the mean of the original distribution was, and it'll move over, by whatever the y-intercept is as well. So the mean or expected value of y is just the mean of the original distribution times b added to a. Now, the standard deviation is a little bit different, right? If you remember back what we discussed in Chapter 6, that adding something to a data set doesn't move, it moves the data, but it doesn't change the spread of the data. It doesn't make it wider or skinnier. So the A is going to make no difference to standard deviation or standard deviation squared of the standard deviation of the new variable squared will be b squared times the standard deviation of the original. The variance of y is the variance of x times b squared. The A does not affect spread. Always in Chapter 16 stuff, never start with the standard deviation. Always get things to variances because the formulas are all based on variances pretty much. And then you can take the square root in the end to get a standard deviation. So an example, temperature in a dial set temperature controlled bathtub for babies. Variable x has a mean temperature of 34 degrees Celsius with a standard deviation of 2 degrees Celsius. Convert the mean and standard deviation to Fahrenheit degrees. So here's our formula for converting Celsius degrees to Fahrenheit degrees. Fahrenheit is 9/5 C plus 32. And so the mean, we're just going to, basically plug in the mean into this equation here. And so we'll have 9/5 times 34 plus 32. So the mean we would expect to be 93.2 degrees Fahrenheit. Now to calculate the spread, though, we use, the spread formula. And so that would be b squared, which is 9/5 squared, right? So that would be 81/25 times the standard deviation squared. That would be 2 squared, or 4. So that's 12.96. Take the square root of that, and we get a standard deviation of 3.6 degrees Fahrenheit. Okay? All right, moving on to the next slide. What about combining different random variables? Okay, so like if we have random variable x, which has to do with something in Celsius degrees, random variable y, which has something to do with Fahrenheit degrees, or maybe, just completely different random variables, but for some reason we're combining them. So adding, subtracting two different random variables, x and y, the expected values will just add if we're adding the two random variables, and the expected values will just subtract if we're subtracting the random variables. Now the variances in both cases will add. Right, the analogy I'd given here as to why they add in both cases was like a box of cereal. Variance is, a measure of spread, kind of related to uncertainty. If you have, an unknown amount of cereal in the box to begin with, maybe that's what your random variable x is about, how much cereal's in the box. There's a little uncertainty to that. And then you're going to pour out a certain amount of cereal. So, that's maybe random variable y, how much you pour out. Okay, there's a little uncertainty here, a little uncertainty here. When you're not sure how much you started with and you're not sure how much you poured out, you're even more uncertain than to begin with. So your uncertainty will increase. So the variances need to add. Remember to take the square root at the very end to find the standard deviation. So if you want the standard deviation of x plus y, take the variance of x plus the variance of y, get your equals, and then take the square root. And so on. Same thing for the subtraction. Okay. One important distinction: if you have two different random variables, x1 and x2, that's not the same as 2 times a single random variable x. Let's look at an example. Let's say x is a random variable for the amount of a bet. X plus x may represent two $1 bets. 2x may represent a single $2 bet. Let's say the expected winnings from one $1 bet is 25 cents loss with a standard deviation of 10 cents. Expected values may come out the same either way, but variances and standard deviations probably won't come out the same. So if we just use our formulas for adding the two different random variables for two $1 bets, we're going to get EX plus EY, that's going to be 0.5, right? Or if we're doing a single $2 bet, that would be 2 times 0.25. That's still 0.5. So the expected values are the same whether we're doing random variable x plus random variable x, or if we're doing 2 times a single random variable x. But let's look at the equations for the standard deviation, right? So if we have a single random variable and we're multiplying it by 2, so that's 2 squared times the standard deviation squared, 0.1 squared, that's 0.2. But if we're having two different random variables and we're adding them, then the variances would be 0.1 squared. And so we need to add those. 0.1 squared plus 0.1 squared, which is 0.04. Okay, and then when you take the square root of that, you get 0.141. So you get different answers here. Here you get 0.2, and here you get 0.141 when you take the square root. So the variances are going to come out different. You can see pages 315 to pages 318 for examples of working with these formulas. All right, so that was chapter 16 in a nutshell, and I hope that helped. We're done.